Okay, so good morning. Today we're looking at gas laws. When you were here, we did look at Charles' law, Bohr's law, and also the Avogadro's law. So try to revise on those so that even as we proceed, you do not have challenges understanding what we're going to be talking about. So today we're looking at Dalton's law of fascial pressures. So this law basically says the total pressure. So the total pressure of a mixture of gases equals the sum. Okay, the sum of the partial pressures of the individual gases in a mixture. That is in a mixture. So if we want to calculate the partial pressure, the total pressure in a mixture of a gas, what we want to do is to add up the individual pressures of the gases in a mixture, and then what we're going to have will be the total pressure of that mixture. Therefore, mathematically, we can say that the total pressure, which is abbreviated as PT, is equal to the partial pressure of gas A plus the partial pressure of gas B plus the partial pressure of gas C. This is assuming that we have three gases. Now, this means that the PT here will represent the total partial pressure of gas B plus the partial pressure of gas C. This is assuming that we have three gases. Now, this is equivalent. This means that the pressure that is exerted here will represent the total partial pressure of partial pressure of gas A, and therefore this will be the partial pressure of gas C, which will be this is assuming that we have three gases, gas B. Now, and then this is equivalent. This means that the pressure that is exerted here will represent the total partial pressure with sum of partial pressure of gas A, and therefore this will be the partial pressure of gas C, which this is assuming that partial pressure have basically three gases, gas B. Now, and then this is equivalent. This means that the pressure that is exerted here will represent the total partial pressure mixture with sum of partial pressure of gas A, and therefore this will be the partial pressure of gas C, which this is assuming that partial pressure have basically three gases, gas Now, and then this is equivalent. This means that the pressure that is exerted here will represent the total partial pressure mixture with sum of partial pressure of gas A, and therefore this will be the partial pressure of gas C, which this is assuming that partial pressure have basically three gases, gas Now, and then this is equivalent. This means that the pressure that is exerted here will represent the total partial pressure mixture with sum of partial pressure of gas A, and therefore this will be the partial pressure of gas C, which this is assuming that partial pressure have basically three gases, gas Now, And then this equivalent means that the pressure PT that is here represents the total molecular pressure in the mixture with some partial pressure, and therefore this is the partial pressure PVC, which is assuming that partial pressure has basically gases now. And then this equivalent means that the pressure PT that is here represents the total molecular pressure in the mixture with some partial pressure, and therefore this is the partial pressure PVC, which is assuming that partial pressure has basically gases now. And then this equivalent means that the pressure PT that is here represents the total molecular pressure in the mixture with some partial pressure, and therefore this is the partial pressure PVC, which is assuming that partial pressure has basically gases now. And then this equivalent means that the pressure PT that is here represents the total molecular pressure in the mixture with some partial pressure, and therefore this is the partial pressure PVC, which is assuming that partial pressure has basically gases now. And then this equivalent means that the pressure PT that is here represents the total molecular pressure in the mixture with some partial pressure, and therefore this is the partial pressure PVC, which is assuming that partial pressure has basically gases now. And then this equivalent means that the pressure PT that is here represents the total molecular pressure in the mixture with some partial pressure, and therefore this is the partial pressure PVC, which is assuming that partial pressure has basically gases now. And then this equivalent means that the pressure PT that is here represents the total molecular pressure in the mixture with some partial pressure, and therefore this is the partial pressure PVC, which is assuming that partial pressure has basically gases now. And then this equivalent means that the pressure PT that is here represents the total molecular pressure in the mixture with some partial pressure, and therefore this is the partial pressure PVC, which is assuming that partial pressure has basically gases now. And then this equivalent means that the pressure PT that is here represents the total molecular pressure in the mixture with some partial pressure, and therefore this is the partial pressure PVC, which is assuming that partial pressure has basically gases now. And then this equivalent means that the pressure PT that is here represents the total molecular pressure in the mixture with some partial pressure, and therefore this is the partial pressure PVC, which is assuming that partial pressure has basically gases now. And then this equivalent means that the pressure PT that is here represents the total molecular pressure in the mixture with some partial pressure, and therefore this is the partial pressure PVC, which is assuming that partial pressure has basically gases now. And then this equivalent means that the pressure PT that is here represents the total molecular pressure in the mixture with some partial pressure, and therefore this is the partial pressure PVC, which is assuming that partial pressure has basically gases now. And then this equivalent means that the pressure PT that is here represents the total is equal to N over N total. Okay? Meaning that for us to calculate the partial pressure, going to say, or this you can do as the mole fraction of A is equal to the partial pressure of A over the total partial pressure. Meaning that, so for us to calculate the partial pressure, where PA is the partial pressure of A, we are going to say that is the partial pressure of A, or this can do PT as the mole fraction of A, the total pressure equal to the partial pressure of A over. So here what we are trying to do is partial pressure. We are saying that you can calculate the mole fraction from the number of moles of gas A divided by the total number of moles within the container or the mixture, which is the partial pressure abbreviated as X of A. PT is equal to A of A, which is number of moles of A divided by the total. So here what we are trying to do is the mixture. We are saying that we can also calculate the mole fraction using the partial pressures, or if you are given pressure, so the pressure, the partial pressure of the container divided by the total pressure is the mixture, is also able to give you the mole fraction of A. So I've said there are three ways in which you can calculate the total, the partial pressures in gases. One is to just use the Dalton of partial pressure, which actually just gives the pressure. The total pressure in the mixture is the sum of the partial pressures of the gases. Yes, so meaning that the total partial pressure is equal to the partial pressure of gas A as the mole fraction also gas. So I've said then we can also use the ideal gas equation, which actually gases. One is concerned ideal gases, and last time we actually just did missing the lecture. For those that in mixture, we look at P partial pressures and RT. And therefore, by substituting the pressure there, since we want to calculate the total partial pressure, then we can actually substitute. And we can also use the ideal gas equation for the partial pressures. Now, let's just look at an example. Try and read this one. So, let's say you have a question. I think this example is also there in notes. So, a tank contains pressure. Now, let's just look at 480.0 grams of oxygen. So this is oxygen there. You have a question and 80.00 grams. I think this example is also there of helium. So a tank attains the total pressure 480.0 grams of 7.00 atmosphere. So this is the atmosphere. And 80.0. So the question is calculate helium. The partial pressure. So that is the partial pressure 480 of each gas of 7.00 atmosphere in the tank. So this is well, that is the question that we want to look at. So we're saying the tank contains 480 grams of oxygen gas and 80.0 grams of helium. So that is at a total pressure of 7.0 atmospheres. Calculate the individual partial pressures of these gases in the tank. So the solution here is to first of all understand that we want to look at. So we're saying is to first of all understand what is given and then work around to get what is not given. So here what we are given is the mass of the gases. So from the mass of the gases we know that we can get the number of the individual partial pressures of these gases. You can get the number here is to first of all moles of the gases. Once we get the number of moles of the gases, then we can be able to calculate what partial pressure. So here what is given is the mass of the gases. Fraction. So from the mass of the gases, here we are saying that first of all, number one, calculate partial pressures of these gases. Number of moles here is first of all. So the number of moles of oxygen gas is equal to the mass of oxygen given divided by its molecular mass. So here the given mass here for oxygen is 480. So here we are saying that first of all grams divided by the molecular mass of oxygen is 16 by 2, which is 32 grams per mole. The number of moles of oxygen, so using that we can be able to get oxygen given the dividend. So in this case, this will give us 15. The given mass here, then the number of moles is 400 helium. Number of moles of helium also is mass over the molecular mass, which is equal to 80.0 grams divided by that. The molecular mass for helium gets 4.0 grams per the dividend. So in this case, this will be dividing those, we are going to get 20. Then the number of moles is 400. So once we get the number of moles there, then we can use the mole fraction of each of these gases to calculate the partial pressure. So let's move to the other side of the board. So here the partial pressure of oxygen. So we are saying the partial pressure of oxygen. So PO2. So the partial pressure of oxygen is equal to here the number of moles of oxygen divided by the total number of moles, which is NT, multiplied by the total pressure within the mixture. So here we are saying that N total, which is the number of moles within the mixture, will be the sum of number of moles of oxygen plus number of moles of helium. So there you have 15 plus 20, which is equal to 35 moles. So that is the total number of moles in that mixture. Therefore, the partial pressure of oxygen is equal to number of moles of oxygen as calculated there is 15 moles divided by the total number of moles is 35 moles multiplied by the total pressure. The total pressure that is given in the question there is 7.0 atmospheres. So we have 7.0 atmospheres. So when you do the simplification there, you're supposed to get about 3 atmospheres for the partial pressure of oxygen. Okay? Then the partial pressure of helium. So the partial pressure of helium is equal to number of moles of helium divided by the total number of moles within the mixture multiplied by the total pressure in the mixture. So number of moles of helium calculated is 20 moles divided by the total number of moles is 35 moles multiplied by 7.0 atmospheres given. Then what we get is 4 atmospheres. Okay, so again, Dalton's law of partial pressures demands that the sum of the partial pressures of the gases in the mixture must actually sum up to the total. So in this case, the total pressure within the mixture we can check from our calculations, we should get a total of 7.0 atmospheres. So we have partial pressure of oxygen plus partial pressure of helium. They should give us 7 atmospheres. So here we have 3 atmospheres plus 4 atmospheres. The total we are getting is 7 atmospheres, which actually was the given total partial pressure. So that is how you calculate the partial pressure of a gas. Okay.
So we actually had some disruption for the first few minutes. Most of them are not coordinated. It was done. It was echoing.
Oh, okay.
Yes, so I had to.
And now it's fine.
Yes, so I had to go out and we changed some of them in the end.
Okay. I think we can just unmute.
Okay.
So which part was I in?
Some did not actually get the introduction.
Okay.
Okay.
Okay, so I've just been made aware that we had some sound disruption. I hope this time I'm audible. Okay. So I'll try and do another, just a small recap on what I've said in the past 20 minutes, and then we can proceed. So we started by looking at Dalton's law of partial pressures. So I mentioned that Dalton's law of partial pressures just emphasizes the fact that the total pressure within the mixture will be the sum of the partial pressures of the gases within that mixture. Therefore, if you are doing some calculations, there are 3 ways you can use to calculate the partial pressure of either the individual gases, or you can calculate the total partial pressure depending on what is being asked. So number 1, we are saying using just the Dalton's law, which states that the sum of the total pressure within the container will be equal to the sum of the partial pressures of the gas. So the PT is total pressure, will be equal to the partial pressure of gas A, for example, plus partial pressure of gas B plus the partial pressure of gas C. But if you have more than 3 gases, then you have gas D, gas E, gas F. So we're just using these abbreviations. So the PA, the A is a subscript, so the B is a subscript, and so on and so forth. So these are actually just representing the partial pressures. So this is one way you can calculate the total pressure within the container. Number 2 is to use the ideal gas equation. Now the ideal gas equation is PV is equal to nRT, where P is the pressure, V is the volume, N is the number of moles, R is the constant, and T is just temperature in kelvins. Okay, now the ideal gas equation comes from a combination of the 3 gas laws that we discussed when we were here. Just a few people used to attend those lectures, but we did cover them. So in your spare time, you could try and recap on Bohr's law, Charles' law, and also Avogadro's law. So try to read on these three laws so that you can be able to understand where we are getting the ideal gas equation. Now, using the ideal gas equation, we are saying that the total pressure within the mixture, we can actually calculate it because we already have the formula here. Therefore, if we solve for pressure, we are saying P is equal to nRT. Now, if the pressure is the total pressure, then the number of moles, will also be the total number of moles. Therefore, we can say that total pressure is equal to total number of moles divided by R, multiplied by R and T, and then divided by the volume. Meaning that if the total pressure is a sum of the partial pressures, then we can say that this will actually be equal to the summation of these partial pressures. Now, each one of these is equal to that, meaning that we can actually say the partial pressure of A will be equal to number of moles of A multiplied by R T divided by V plus total number of, let me just write this side so that you can see it. So that would be equal to number of moles of A RT over V, that is volume of A, plus number of moles of B, RT divided by volume of B, plus number of moles of C, RT divided by volume of C. So this you can use also to calculate the partial pressures. The third type of, or the third way you can calculate the partial pressures is to use the mole fractions. Okay. Now the mole fraction is basically just a mole fraction, meaning that you have a number of moles of a gas divided by total number of moles in the container. So total moles in the container. Meaning that if you are discussing the mole fraction of A, we are saying mole fraction of A, let me use a capital letter, is equal to number of moles of A divided by the total number of moles, which is NT. Okay. Now, since we are calculating the pressure, we can say that therefore the partial pressure of A will be actually calculated also using the mole fraction. In this case, we can say that this is equivalent to the mole fraction of A is equal to the partial pressure of A over the total pressure. So in this case, what we are trying to do is to say that you can calculate the mole fraction using the number of moles or using pressure. So if you are given pressure, you can still calculate the number of moles, and also, or rather you can calculate the mole fraction. Meaning that if you have, in this case, a number of gas fractions, it means that the sum of all mole fractions should always be equal to 1 because they are fractions. Okay, so in this case, what we are saying is that the mole fraction of A plus the mole fraction of B plus the mole fraction of C should be equal to 1. Sometimes you can be given a question that is in terms of percentages. So the percentages could actually be the mole fraction. So if I say gas A is 35%, gas B 25%, what would be the mole ratio of gas C? What you will just need to do is to add the two. 35 plus 25 will give you 60, meaning that gas C is 40%. Now, as a fraction, 35 is 0.35, 25 is 0.25, and 40 is 0.4. And then we did give a question which we calculated earlier on. But for the sake of those of us who missed on the volume, we can try to give another example. So let's say example 2. So I'm sure all of us now are on the same page and therefore can move. Again, here we have a storage tank, contains 2 moles of argon, 3 moles of oxygen gas, and 5 moles of nitrogen, which is N2, at a total pressure of 1,000 torrs. Okay. Calculate the partial pressure of each gas in the container. Okay. So the first thing that we have to do here is to identify that we have been given certain things in the question, and those are the things that we need to use. Okay. So it's very easy to do that. Okay. So within the question here, our life has been made very easy because we've been given already the number of moles of each gas. Therefore, what we just need to do is to get the mole fraction of each gas and then use the total pressure to calculate for each one of them. Therefore, here what we have to do is, number 1, calculate the mole fraction of each gas. Then number 2, use the mole fraction and the total pressure to calculate the partial pressure of each gas. So to calculate the partial pressure. So as simple as that. So we start with the first gas that is given, which is argon. So we are saying the mole fraction of argon. So the mole fraction of argon is equal to the number of moles of argon divided by the total number of moles, which is NT. Okay. That is the mole fraction. So here, remember that the number of moles is given. Therefore, NT in our case will be equal to number of moles of argon plus number of moles of oxygen plus number of moles of nitrogen, which is N2. So this will be equal to 2 plus 3 plus 5, which is equal to 10 moles. So that is the total number of moles for that. So what we are doing here will be number of moles of argon will be 2 over 10, which is equal to 0.2. So that is the mole fraction. Now to get the partial pressure of argon, which is PA, PR, okay, this will be equal to the mole fraction of argon times the total pressure in the container, which is P total. Okay, so that will actually mean that the mole fraction of argon is 0.2 times the total pressure in the container is 1,000 torrs. Therefore, the partial pressure of argon is 0.2 times 1,000, which is 200 torrs. Okay, so that is the partial pressure of argon. Let's calculate the partial pressure of oxygen. Okay. So we come this side. So we are saying the first thing again that we do for oxygen is to calculate the mole fraction. So the mole fraction of oxygen is equal to number of moles of oxygen divided by the number of moles in the container, which is the total number of moles. So what we're going to have there is number of moles of oxygen is 3/10. So that will be equal to 0.3. Therefore, the partial pressure of oxygen, okay. So the partial pressure of oxygen, which is PA, so which is P oxygen is equal to, which is the pressure of oxygen is equal to 0.3 times 1000 torrs, which is going to be 300 torrs. Then to calculate for the partial pressure of of nitrogen, again we have to calculate the mole fraction. So the mole fraction in this case for nitrogen is going to be equal to number of moles of nitrogen gas divided by the total. So the number of moles of nitrogen are 5 divided by 10, that will be 0.5. The partial pressure of nitrogen will be equal to the mole fraction of nitrogen times the total pressure, which is total pressure PT. So that will be 0.5 times 1000 torrs, which is equal to 500 torrs. So that is how you calculate the partial pressures of gases within a mixture. One thing that you have to remember is that the partial pressures of individual gases must add up to the total total pressure within the mixture. So in this case, we expect that the addition of these partial pressures for these gases should be equal to 1000. So you can actually check our calculation if it is correct. So 500 plus 300 plus 200, we get 1000 torrs. So that is how you calculate the partial pressures. Let's move on to what is known as Graham's law. So Graham's law states that the rate of diffusion of a gas is inversely related to the square root of its molar mass. So what this means is that the rate of movement or diffusion of a gas is going to vary inversely with the square root of its mass. In this case, actually, what this means is that if you have a gas that is heavier, you expect the rate to be slower. That is inversely. If a gas is lighter in terms of weight, you expect that the rate is going to be faster. So here, if we have gas A and gas B, we can relate their rate based on some kind of ratio. So let's say the ratio of gas A speed to gas B speed can be related in an equation. And this equation is, if we are using speed, we can say rate, so the R is for rate. So rate of gas A over rate of gas B is equal to the square root of the mass, molar mass of B divided by the molar mass of A. Okay. Now you can see here that we have switched the masses and the rate. So here the numerator is A, here the denominator is the mass of A. So just take note of that. So we are saying where R is the rate of the gas. So in this case, RA is the rate of gas A, RB is the rate of gas B. And then where M, we are saying that this is the molar mass of the gas. Okay. Now, there are certain key terms that are used in Graham's law. So we have one is the common one, which we all know is diffusion. So diffusion is the movement of gas particles, in this case, since we are talking about gas particles, from a region of high to low concentration. So this one is well known, it's just movement of gas particles from high to low. Then we have another term which is effusion. So effusion is the diffusion of gas particles through an opening that is through an opening in a container. So the rate of movement of either diffusion or effusion can be actually studied. In this case, the rate of effusion also is actually inversely proportional. So the rate of effusion is equally inversely proportional to the molar mass of the gas. So for gases, the rate of diffusion, and here we can say for gases, the rate of both diffusion and effusion follow Graham's law. Meaning that we can use this law to predict basically what you need to expect in an event where you are given a question that deals with gases. So if you are given a gas, depending on its weight, you have to compare with another one. It means that the one with the lighter mass, you expect it to effuse quickly. The one with the larger mass will have to actually move out of the container much slower. Okay, so that is rate. So in this case, we are saying the larger molecules with the larger mass will actually be slow. We expect them to be slow. And then the ones that have a less mass, we expect them to be faster or fast. Okay. What does this mean? This means that as the mass of a gas increases, so as mass of the gas increases, its effusion should decrease. So its effusion decreases. So that is what we expect to be seen. Okay. Let's look at an example of a question that you have on Graham's law. Okay. So an example. So the rate of effusion of argon was measured at 0.218 moles per second at 37 degrees Celsius. Calculate the rate of effusion for helium at the same temperature. Or we can just end here and say calculate the rate of effusion for helium gas. Like that. Okay. So here what we want to do is, first of all, to identify that for us to solve this question, we are just going to use the simple formula. R1 over R2 is equal to the square root of the molar mass of gas 2 over the molar mass of gas 1. Now here let us say R1 will be the rate of helium. Let's put R1 to be helium and R2 to be argon. Therefore, this means that we'll have rate of helium over rate of argon is equal to the square root of the molar mass of argon divided by the molar mass of helium. Okay. So the rate of helium is not given, so we are getting to find out the rate of helium. So what we have is RHE, rate of helium, we don't know, but the rate of argon is given here. So 0.218. I can leave out the units for now, is equal to the square root of the mass of argon. So the mass of argon is 40 divided by the mass of helium is, the molar mass of helium is 4.0. Okay? So if we can come here, from there, if we simplify that, we are going to have rate of helium is equal to, that is divided by 0.218 is equal to, if we simplify that, we are going to have 3.162. Let's make it a ratio divided by 1. Okay? If we cross multiply, what we are going to have is rate of helium is equal to 0.6894 moles per second, which translates to about 0.689. We are given to 3 decimal places here, so we can also report to 3 decimal places, moles per second. Okay, so that would be the rate of helium. Now, when you look at the calculation that we've done, you can actually see that the rate of helium is much, so since helium is lighter than argon, it has a higher rate of effusion. So you can see that argon, which has a larger mass of 40, has an effusion rate of 0.218, but helium, which is lighter, has got a higher rate of effusion, meaning that if the two are placed in a container, you expect helium to completely move out of the container much faster than the argon. Let's have another example here of the question. So it takes 53.12 seconds. So that is another example on the same Graham law. So it takes 53.12 seconds for a sample of carbon dioxide to effuse from one compartment into another at a set temperature. So that is at a set temperature. Determine the time. So determine the time it would take neon to do the same job. So here what you have is carbon dioxide and neon. You are given the rate of, or rather the time taken for carbon dioxide to move from one compartment of a container into another. Now the question is, can we determine the time that it would take for neon to do the same job? Now this is a different type of question. You will note here that what we have been using so far is the rate. So the rate is the amount consumed per second or per minute. In this case, we are just given time. Now, one key thing that we have to note here is that heavy gas molecules move slower. So the key here is to identify the fact that heavy gas molecules are slower. Therefore, they take more time. They take more time. It's important to take note of that. Then lighter gas molecules, these are faster. Therefore, they take less time. That is less time to move. So it's like movement of vehicles between a truck and a car. All things being constant, assuming that all vehicles are in tip-top condition, you expect that the car will move faster than a truck, which is a heavy vehicle. Okay. Now, based on that, we can actually come up with key statistics here. And these key statistics are basically going to help us to try and solve this question. So in this case, what we are saying is that when the mass of the gas molecules increase, so when the mass goes up, what happens to the rate? The rate will go down. Okay? So the rate of movement for the gas will go down, or rather it slows down. But what happens to the time spent? Okay, the time that is spent to do the job, it goes up. So time goes up or increases, it's short. So that increases. Now, that being the case, okay, now when you compare rate and mass, we said that these two are inversely proportional. But when you look at mass and time, these are actually going in the same direction. When the mass increases, the time that is needed to do the job increases also. So in this case, therefore, it means that our equation that relates mass and time is actually going to be a little bit different from the one that relates mass and rate, which we were looking at. Therefore, if we have T1 for gas 1 over T2 for gas 2, this will be actually related to their mass in the same way as they are written. And therefore, that will be M1 over M2. The reason is that these are directly proportionally related. When the mass increases of the gas molecule, it means that they become slower, therefore they will take time to move to the next compartment. If the mass is much lower, then it means that the gas will take less time to move to the other compartment. Therefore, looking at our question, therefore we can use this, this equation and say T1 let's call T1 to be carbon dioxide. So T1 is carbon dioxide. Then let's say T2 is neon. Okay. Having done that, we can substitute what we are given. So for T1 is for carbon dioxide, which is given. So we can say 53.12 seconds divided by, we are looking for time here. Determine the time it would take for neon. So time for neon is not yet known. So that will be equal to the square root the mass of carbon dioxide. So the molar mass of carbon dioxide, you can calculate it quickly. That is 12 plus 2 by 16. So that is 12 plus 2 by 16 is 32. So we have 44. That is the mass of carbon dioxide. So we can place it in the equation there. 44 divided by the molar mass of neon is actually 20.18. You can check that on the periodic table. So what you're going to have therefore is the square root of 2.18. So here, I don't want to go this side because the camera seems not to be following me. But what we have this side, okay, so it's still visible. So what we're going to have is 53.12 divided by the time for neon, which will be equal to, when you simplify what we had that side, 44 over 20.18, and then you divide that, you're going to get 2.18. So when you square root that, you should get 1.47648. So 1.47648, which translates to 53.12 over T of neon is equal to 1.47648. Make Tn the subject of the formula. What you're going to have is actually Tne is equal to 53.12 divided by 1.47648. When you simplify that, what you're going to get is 35.977 seconds. We have seconds there. Okay, so when we round that up, we are going to have 35.98 seconds. Okay, so if you analyze what you have gotten there, the time for neon and the time for carbon dioxide, you will notice that this actually also follows Graham's law, in that we can actually predict. So carbon dioxide, which has a larger mass, which is 44 grams per mole, takes more time, which is 53.12 seconds, to cover the same distance, okay, compared to neon. Neon, which is weighing 20.18, takes about 35.98 seconds. So you can actually check here that since carbon dioxide is heavier than neon, it takes longer. So carbon dioxide, which is heavier than neon, takes much longer time to cover the same distance, or rather the same job. Okay. Okay. Let's look at the kinetic molecular theory. Now, I'll not spend too much time on the kinetic molecular theory, because this you can actually read it in the notes. It's a little bit straightforward. The notes are there on Moodle. So you can just revise on that and just fine tune. That is the kinetic molecular theory, which is abbreviated as KMT, like that. So this is given in the notes, straightforward. There isn't so much to discuss. But this is actually based on the idea that particles of matter are always in motion, which is continuous motion. And it actually provides a model for what is called an ideal gas. So this provides a model for the ideal gas. Okay, so an ideal gas basically may be a real gas or not. Okay, so an ideal gas is an imaginary gas that perfectly fills all assumptions of the kinetic molecular theory. So this ideal gas is imaginary. It's an imaginary gas, and it fulfills, or rather it fills up all the assumptions that are postulated under the kinetic molecular theory. Okay. Now the postulates of the kinetic molecular theory, you can check them out on Moodle. Like I said, they are basically straightforward, and it just says gases consist of tiny particles. The particles are small compared to the distances. The particles are assumed not to attract or repel each other. And also the kinetic molecular theory is directly proportional to the Kelvin temperature of a gas. So that you can read in your own time. And then also you have to know the differences between an ideal gas and a real gas. Okay. So an ideal gas, remember we have said, is an imaginary gas. A real gas is a real gas, like carbon dioxide and so on and so forth. You may also want to know at which conditions do these real gases actually exhibit ideal gas properties, for example. Okay, so you can try and understand that. So finally, in this lecture, let's look at the van der Waals equation. I'm sure this word, van der Waals, has not come as a new word. We've come across what are known as van der Waals forces, and so this is not a new concept. But van der Waals equation is based on plausible reasons so it's based on reasons that real gases do not follow, so they do not follow the ideal gas law. The ideal gas law at all pressures and temperatures. So the real gases do not follow the ideal gas laws at all pressures and also temperatures. Therefore, the ideal gas law is not exact in dealing with these real gases, although it is very accurate in most situations. So if we need super accurate numbers, then we need to use the van der Waals equation. Mostly if you look at the postulates of the kinetic molecular theory, you will find that, for example, we are saying that particles are very small. They are so small compared with the distances between them, that the volume of the individual particle can be assumed to be zero. This is not true for real gases because they actually have a volume, okay? And therefore, if we were to use the ideal postulates here, or the kinetic molecular theory postulates here, we would be getting inaccurate numbers. And that is why we are saying that if we need to have super accurate numbers, then we need to use the van der Waals equation. Now, the van der Waals equation takes into account the changes in volume and also the change in pressure. So what we are doing here is to try and correct the pressure and also the volume so that we have the correct numbers. So in this case, pressure plus AN squared divided by volume squared multiplied by the volume minus NB is equal to nRT. So here we are saying where A in the equation, which is there, accounts for the fact that there are actually intermolecular forces. So intermolecular forces between the particles. Between the particles. B accounts for the fact that molecules actually do take up some amount of volume. So in the equation, the van der Waals equation takes account of the overall effects of the fact that within the gas molecules, the particles actually have some form of intermolecular forces. These could be attractive or repulsive forces. And also B, the fact that these molecules, when they are placed in a container, they actually occupy some form of space. Therefore, A and B, in this case, account for the overall. So this accounts for the overall change that we are seeing. Which is the overall outcome. Okay? So under the ideal gas equation, which is, or rather the kinetic molecular theory, the postulates are that these gases do not attract or repel each other, and that they have zero volume. Okay? So they do not occupy volume. But that is not the case, like we are saying. So this is to account for the volume change, and also to account for the fact that these molecules actually do attract. So if they are repelling, they are going to affect the volume. If they are attracting, still more, they are going to affect the volume. So let's have an example to just try and see how the van der Waals equation can be utilized. So as an example, we can say calculate the pressure exerted by 0.300 moles of acetic acid in a 3-liter container at 40 degrees Celsius using one, or is it A, the ideal gas law, and B, we use Van der Waals equation. Now, using Van der Waals equation, we are given A to be equal to 17.71 atmospheres per liter squared. So 1 atmospheres liter squared, that is per mole squared. And B is equal to 0.237 liters, that is per mole. Okay? So remember that for the Van der Waals equation, we have P plus AN squared divided by V squared multiplied by V minus NB is equal to nRT. Okay, so the question is saying A, using the ideal gas equation, and B, using the Van der Waals equation. So A, using the ideal gas law, we are using the ideal gas equation. So we know that PV is equal to nRT. Here, we are calculating the pressure. So we are saying where pressure we do not know. The volume is given is 3.0 liters. What else are we given? Number of moles is 0.3 moles. What else are we given? The R constant, we are going to be directed which R constant to use out of the many by the temperature, I mean the pressure that we want to get. So in this case, using what is given on the Van der Waals equation, we can use atmospheres. So we're going to have 0.0823. So 0.08206. And then the units are always given. Then the temperature, we are given at 40 degrees. Remember that the temperature must always be in kelvins. So we are going to add plus 273. So that will be equal to about 313 kelvins. Okay. So having done that, then we can calculate for the pressure. So P is equal to nRT over V, which is equal to N is 0.3 times the R constant 0.08206 multiplied by temperature 313 divided by the volume, which is 3.0. If you simplify that, what you are going to get is about 3.85, that is 3.85 atmospheres. That is using the ideal gas equation. Okay. If we use the Van der Waals equation, So B, if I came there, so I'm saying P plus AN squared over V squared, V minus NB, and nRT, or rather is equal to nRT, like that. So the pressure we do not know, but if we were to solve for P, which makes our life very easy, if we have to solve for pressure, what we can do is just to simplify this. We are going to say P plus AN squared over V squared is equal to nRT divided by, so this is taken the other side by dividing both sides, so we have V minus NB. Okay. So if we take the other unit, the other side, this, so if we put this side, take that to the other side, what we are going to have is P is equal to nRT divided by V minus NB minus AN squared divided by V squared. Okay. Having done that, we can just substitute in the formula. Instead of going the other side, allow me to come this way. So allow me to bring this this calculation this side. So I'll just rewrite it. So I'll just say P is equal to nRT divided by V minus NB minus AN squared divided by V squared. So this will be equal to N in our question has been given to be 0.3 moles. So 0.3 times the R constant that we used there was 0.08206 times the temperature was 313 divided by the volume 3 liters minus the number of moles 0.3 multiplied by the value of B which we've been given. So the B was 0.0237, that is liters per mole. So since this is liters per mole, the moles will cancel, and then minus, so we have minus there. The value of A which we were given was 17.71 multiplied by N squared, so N is number of moles which is 0.3 squared, 0.3 squared divided by the volume squared. So the volume is 3, so 3 squared. So we have that, like that, simplified. So if you do that, what you're going to get is 7.705 divided by 1.993 minus 0.398. So when you simplify that, you should be able to get this side 3.87 minus 0.398. The difference is equal to 3.47 atmospheres. Okay, or ATMs. Now, when you compare the pressures that you have calculated, so using the ideal gas equation and the van der Waals equation, you can see that the ideal gas equation gives you a volume which, gives you a pressure which is much higher than what you get when you correct using the van der Waals equation. And therefore, this is why when you are dealing with a real gas, which actually has interaction of particles or gas particles, it's a bit different compared to an ideal gas, because an ideal gas, you assume that in this case, what you are getting or what you have is negligible volume, or rather no volume. Secondly, you assume that actually these gas molecules have got no attractive properties and no repulsive forces. So looking at these figures that we have gotten, a pressure of 3.47 for the van der Waals equation, which actually represents more or less like the real gases and the ideal gas. So those differences are what Johannes van der Waals tried to rectify. And this guy actually won a Nobel Prize for this discovery. So for today's lecture, for this first session, we'll end here. Then in the afternoon, we are going to discuss actually chemical bonding. So thank you so much for your time.